So how can we prove that TFL is in fact sound? Let's start by reviewing some core concepts. TFL is sound if and only if we can prove only tautologically valid arguments. That means that if there is a proof of a conclusion C from premises A1 to AN, then the argument from A1 to AN to conclusion C is tautologically valid, which means, in other words, that every valuation that makes all of these premises true also makes the conclusion true. So that's what it means for TFL to be sound. And we also said that we are going to prove that TFL is sound by means of an inductive proof. Inductive proofs have a lot to do with inductive definitions. We have already encountered several inductive definitions, for example, the definition of a TFL sentence. An inductive definition first starts with a base case. We say, for example, all the atomic sentences are sentences. And then we are proceeding to an inductive step where we lay down rules for expanding our base class of entities. So in the case of a TFL, the definition of a TFL sentence, we said that you can use the Boolean connectives to construct further sentences out of the atomic sentences. And then finally, an inductive definition includes a that's it clause. So we say nothing else is a TFL sentence. Now, inductive proofs are in a way based on inductive definitions. We first prove that all the entities in our base class have a property P, and then we prove that if we expand this base class of entities according to certain rules, then every element of the expanded class also has property P. So this was review. We have talked about this in detail in the last part of this lecture. Let's think about what that means for the proof that TFL is sound. We have talked a lot about TFL proofs, but we do not yet have an inductive definition of what a TFL proof is. So let's start by giving an inductive definition of a TFL proof. For the base case, we are going to stipulate the following. Every sequence of n+1 TFL sentences, where the first n sentences are premises and the n+1st sentence is inferred by a correct application of one of the 12 basic inference rules, is a TFL proof. So in short, every proof where just one line is inferred is a TFL proof. That's our base class, the class of the shortest possible proofs. And then we go on to define if P is a TFL proof, and we add to P either a premise or a line that is justified by a correct application of one of the 12 basic inference rules. The result is again a TFL proof. So here the idea is just take a TFL proof and add a line to it, where this additional line is either a premise or justified by one of our 12 basic inference rules. And then the result again is a TFL proof. And finally, we say nothing else is a TFL proof. So every TFL proof either falls in our base class of entities or is defined in our inductive step, and nothing else is a TFL proof. Now, based on this inductive definition of what a TFL proof is, we can now prove that TFL is sound. And to this end, we are going to proceed in two steps. In the base case, we will first show that the shortest possible proofs with just one inferred line are proofs of tautologically valid arguments. And for the inductive step, we will then assume that proofs up until line n are proofs of tautologically valid arguments. That's our inductive hypothesis. And based on this inductive hypothesis, we then show that if we add a line to such a proof, the result is again a proof of a tautologically valid argument. And together the base case and the inductive step entail that every possible TFL proof is the proof of a tautologically valid argument. So let's think about both the base case and the inductive step more carefully. In the base case, we need to show that if a line is inferred by one of our 12 basic inference rules, then every valuation that makes all premises of the proof true also makes this inferred line true. Now, in order to show this, we need to look at all of our 12 basic inference rules separately. So these rules are conjunction introduction and elimination, conditional introduction and elimination, biconditional introduction and elimination, disjunction introduction and elimination, bottom introduction and elimination, negation introduction and elimination, and indirect proof. I'm not going to go through all of these rules here. Instead, we are just going to look at a few examples to illustrate how this proof goes. So suppose that the second line in a proof is inferred by, or is justified by means of disjunction introduction. That means that the proof looks like this. We have one line, the first line, which is a premise. It says A, and then in the second line it says A or B, where A or B is justified by means of disjunction introduction. Now, this is a proof in our base class. It is one of the shortest possible proofs. And we can clearly see that this proof is a proof of a tautologically valid argument. Why is that? Well, every valuation that makes the premise A true also makes the disjunction A or B true, given that the truth of A is sufficient for the truth of A or B. And so that means that the argument A, therefore A or B, is tautologically valid. So here we have covered the case disjunction introduction, and we have shown that if you take a proof in our base class of proofs and the one inferred line is justified by means of disjunction introduction, then this proof is a proof of a tautologically valid argument. To look at a second example, suppose again we have a two-line proof where the second line is justified by an application of conjunction elimination. That means that the proof looks like this. In line 1 we have a conjunction, say of the form A and B, and in the second line we have one of the two conjuncts, in this case A, and the second line is justified by means of conjunction elimination applied to line 1. Now this proof again clearly is a proof of a tautologically valid argument, given that every valuation that makes the conjunction A and B true makes both conjuncts A and B, and therefore also the first conjunct A true. So that means that the argument A and B, therefore A, is tautologically valid. So what we have seen here is that this proof, which is also a proof in our base class, one of the shortest possible proofs, is the proof of a tautologically valid argument. Now, to complete the base case of our soundness proof, we would need to look at the 10 remaining inference rules as well. But we are going to leave that as an exercise and not cover each of these rules in this lecture.